There is a tomato plant in a backyard garden in central Virginia. The leaves are green. The cages are tall, the plant looks fine, but the fruit this season is smaller than 3 summers ago. There are fewer of them. Same soil, same seeds, same gardener, less food. If you've been gardening for 5 years, 10 years, 15, you may already recognize this feeling. Not a plant dying dramatically. Not a pest you can point to or a disease you can spray. Just a slow, quiet decline. The kind that gets blamed on the weather, on the season, on getting older. The kind that makes a gardener wonder what they're doing wrong. Nothing is wrong with the gardener. Everything is wrong with the soil. And the damage has been happening for years below the surface before a single plant showed any sign of it. He has tried more fertilizer. He has added compost. He has followed every recommendation in every guide he has ever read. The decline continues. Slow. Baffling. A soil test run on that Virginia garden in the spring would return a number the extension agent would call acceptable. The extension agent would be looking at the wrong metric. This is not a story about one Virginia gardener. It is the story of a cascade, a chain of decisions that began in 1947 and is still playing out in the soil beneath your garden bed right now. And a North Dakota farmer named Gabe Brown, who watched it destroy his land 4 times in 4 years before he was forced, against every instinct, to discover how to reverse it. And the reason most American gardeners have never heard the name of the man who predicted Brown's crisis from soil data 50 years before it happened. The reason that prediction was structurally invisible to every institution positioned to act on it is the part of this story that reframes everything about a bag of synthetic fertilizer sitting on a hardware store shelf. Most American gardeners think of soil the way they think of a gas tank, a growing medium, something to fill, something to maintain, something that runs out and needs to be refilled. Here's the part nobody explains: what soil actually is. What every shovelful pulled from a healthy garden bed actually contains is a living ecosystem so dense that bacteria, fungi, protozoa, nematodes, and microscopic arthropods perform thousands of simultaneous biological reactions in every cubic inch. The plant does not pull nutrients out of the soil. It pulls nutrients out of the organisms living in the soil, bacteria that fix atmospheric nitrogen, fungi that mine phosphorus from rock particles, protozoa whose waste is the form most plants can actually use. The most important of these organisms is one most gardeners have never heard discussed at any garden center: the mycorrhizal network, a web of fungal threads that grow into and around plant roots, extending those roots functionally 100-fold, reaching mineral deposits the plant could never access alone, trading those minerals back to the plant in exchange for sugars from photosynthesis. This is the actual feeding system of every healthy plant in every healthy garden in human history. Synthetic fertilizer bypasses this system entirely. It dissolves directly into the water around the roots. The plant absorbs it. The mycorrhizal network, no longer needed as a delivery mechanism, begins to atrophy. The bacteria that decomposed organic matter and released its bound nutrients begin to decline. The earthworms thin. The soil becomes chemically fed and biologically impoverished. It does not matter that the plant looks fine. The plant is fine. It is the soil that is dying, slowly, invisibly, and it does it so quietly you won't notice until it's already cost you seasons. If your yields have been dropping and you keep reaching for more fertilizer, this is already happening, not a future warning, a current condition. And by the time the damage shows up in smaller fruit and reduced yield, the damage below ground has already been accumulating for years. Between 1947 and today, the average organic matter content of American agricultural topsoil has declined from approximately 3 to 4% to under 1% across most of the Corn Belt. At 3 to 4%, the soil is a living system. At under 1%, it is a growing medium, technically capable of sustaining plants, genuinely incapable of sustaining them the way it once did. That difference is not cosmetic. That difference is what happened to your garden. The microbiologist Dr. Elaine Ingham at Oregon State University has spent decades documenting what she calls the soil food web, the complete network of organisms that turn dead matter, and atmospheric nitrogen into living plant growth. Her research, along with fieldwork documented by geologist David Montgomery in his 2017 book, Growing a Revolution, has produced the clearest picture available of what actually happens in healthy soil, and what stops happening when synthetic inputs replace biological processes. The picture is this: a healthy soil is a living system, performing thousands of simultaneous biological reactions. A depleted soil is an inert medium performing none of them. A plant in healthy soil grows by participating in that system. A plant in depleted soil grows by being fed pre-digested chemicals that arrive in plastic bags. 1 teaspoon of truly healthy soil contains more living organisms than there are people on Earth. The soil in the average American vegetable garden, managed with synthetic inputs for 10 or more years, contains a fraction of that. Not fewer organisms. A fraction. Every season that passes with that fraction intact instead of recovering, the garden is working harder on less. The yields reflect it. The gardener blames themselves. The problem is underground. The cascade that produced that fraction was not random. It was predictable. It was, in fact, predicted. And the person who predicted it, with documented soil data from Missouri fields in the 1950s, is the reason this video exists. In 1947, the United States Department of Agriculture authorized the agricultural distribution of anhydrous ammonia, a compound originally manufactured during World War II for explosives production, retooled in the post-war period for fertilizer use. The chemistry was elegant. Anhydrous ammonia is nitrogen in its most concentrated commercially available form, 82% nitrogen by weight, applied directly to soil through pressurized injection. It was cheap to produce. It was cheap to transport. It worked. The decision to recommend its widespread use was not a conspiracy. It was a reasonable response to a real problem. Nitrogen had been the primary limiting factor in American crop yields for 50 years. Anhydrous ammonia removed that ceiling. Yields increased dramatically, 20, 30, in some cases 40%. Within the first 3 growing seasons after adoption, farmers who tried it produced more food. Farmers who did not lost market share. The 2 German chemists who had originally developed the underlying process, Fritz Haber and Karl Bosch, working between 1909 and 1913, would have been astonished at this application. Their original goal had been military, producing nitrates for explosives without dependence on Chilean saltpeter imports. The fact that the same process had become the foundation of post-war agriculture, on a scale that now feeds approximately half the human population currently alive, is one of the strangest second-order consequences of any 20th century invention. The roots and garden position on the Haber-Bosch process is this. It was one of the most consequential inventions in human history, and it has been used in ways the inventors almost certainly did not foresee. Both things are true. Synthetic nitrogen has prevented mass starvation. It has also produced a soil biology cascade that was visible in Missouri research data within a decade of widespread adoption, and that almost no agricultural extension agent in 1955 would have stopped to consider. The cascade didn't start with a mistake. It started with a solution, and that's exactly why nobody saw the damage coming. But here's where the system started working against you. The fertilizer wasn't actually the problem. The real problem was something nobody was measuring, and by the time they noticed, it was already too late. In 1952, in a soil laboratory at the University of Missouri, a man named William Albrecht had already proven what would happen next, and nobody in a position to act on it was required to care. Now this is where it shifts. Consider William Albrecht in 1952. Not the historical figures cited respectfully in soil science textbooks today, but the working professor in a Missouri laboratory who had already proven what the agricultural establishment did not want to know, and who had no idea his findings would be ignored for the next 52 years before being quietly confirmed in a research journal that did not even cite him by name. Albrecht was chairman of the Department of Soils at the University of Missouri from 1938 to 1959. He spent 4 decades doing what almost no other American soil scientist of his generation was funded to do, measuring the relationship between soil mineral content and the nutritional density of the food grown in that soil. His finding was unsettling. The synthetic nitrogen fields produced larger, heavier, more abundant crops. By every metric the USDA was tracking, they also produced food with measurably lower mineral content than the same fields had produced a decade earlier. More food by weight, less food by value. The bag was getting bigger. The nutrition inside it was shrinking. He knew what was coming. He could measure it in every soil sample that crossed his desk, and he could not stop it. Albrecht published. He presented at conferences. He wrote to colleagues. The data was real, the methods were sound, the conclusions were specific, and his findings were, in the most precise institutional sense, ignored. This was not suppression, and here's the part that should bother you. It's more insidious than that. The agricultural extension system did not need to suppress Albrecht. The system simply had no metric for what he was measuring. Yield per acre, measured. Profit per bushel, measured. Adoption rates of new fertilizer technologies, measured. Nutritional density of harvested crops, not measured. There was no socket on the institutional dashboard for Albrecht's data to plug into. A scientist whose findings have no place to land is, in functional terms, a scientist whose findings have not happened. Albrecht had the data in 1952. The system had no use for it. The cascade continued. He spent his last working years measuring soil samples in a laboratory whose walls would have smelled, faintly, of geosmin, the compound produced by actinobacteria in healthy soil, the molecule responsible for the smell of earth after rain, a measurable indicator of soil biological activity, a signal that what he was studying was real and that it was disappearing. He retired in 1959. He died in 1974. Neither event changed anything the extension program was doing. By the late 1950s, the cascade had begun moving on its own, and at this point, something breaks. Consequence 1, soil organic matter began declining across managed agricultural land. Synthetic nitrogen fed the plant directly. The mycorrhizal network, no longer essential, began to atrophy. The bacteria that had decomposed crop residue began to decline. The earthworm populations began to thin. None of this was visible. None of this affected yield in the short term. The system was eating its own future and producing record harvests in the present. Then came the second decision. The 1960s herbicide revolution eliminated what farmers called weeds. Many of these weeds were doing biological work that nobody had bothered to formally measure. Clover, which had fixed atmospheric nitrogen and had been planted in rotation by every American farmer for 100 years, became a weed to be eliminated. The leguminous ground covers that were the primary biological nitrogen source were replaced by synthetic nitrogen. The biologic pathway was abandoned. The chemical pathway became the only pathway. Here is what nobody said at any agricultural extension meeting in 1965. If we remove every biological process that maintains soil health, we will need to replace each one with a purchased chemical equivalent. This is not because nobody was smart enough to notice. It is because the people who would have said it were measuring nutritional density at the University of Missouri, and the people running the meetings were measuring yield. The meeting room had no window on the soil. And here's where it gets worse. Consequence 2 arrived in the 1970s, monoculture specialization, farms eliminated hedgerows, crop rotation disappeared, livestock integration ended. Each elimination was locally rational. Each elimination removed another biological process the soil could not maintain through chemistry alone. By 1983, the topsoil erosion rate across American agricultural land had reached a level that researchers described in language not typically used in academic publications. The country was losing topsoil annually faster than topsoil had accumulated since the last ice age. The Dust Bowl had been a drought event. This was something else. This was biology, or the absence of it. If your soil feels harder every year, compacts faster, drains slower, you're seeing this in real time, not the farm version, the garden version. Same cascade, smaller scale. Each decision in the cascade was rational at the time. Nobody was making a villainous choice. The system simply produced its own momentum. Each step necessitated the next. Each replacement of a biological process with a chemical input made the next biological process redundant and therefore expendable. 60 years passed. The mechanism never reversed itself. There was no reason it would. At this point, the soil beneath millions of American gardens was not just less productive. It was structurally incapable of being productive without continued chemical intervention. The dependency was complete. The cascade had reached its endpoint, and most of the people gardening in that soil had no idea any of this had happened. Here's the detail that should have ended the argument in 1952, but took 50 more years to arrive. In 2004, more than 3 decades after Albrecht's death, a research team led by Dr. Donald Davis at the University of Texas published a study in the Journal of the American College of Nutrition. The study examined 50 years of USDA data on the nutritional content of 43 vegetables and fruits. The findings: protein content, down 6%, calcium, down 16%, iron, down 15%, vitamin C, down 20%, riboflavin, down 38%, magnesium, down 9%. The decline was consistent across nearly every food crop measured. The yields over the same period had increased substantially. The crops were getting bigger. The nutrition inside them was shrinking, exactly as Albrecht had documented in 1952. The Davis study did not cite Albrecht. The mechanism Davis described had been documented by Albrecht half a century earlier. The recognition arrived. It did not arrive in time to give credit to the man who had been right when nobody wanted him to be. He had the data in 1952. The confirmation arrived in 2004. 52 years. If you're adding more fertilizer and getting less back with every passing season, you're already inside this system. Not at the end of it. Somewhere in the middle of it, which means the arithmetic can still run in the other direction. 52 years of vegetable gardens producing less nutrition with every passing season. 52 years of gardeners reaching for more fertilizer and getting less back. 52 years of a problem that was documented, ignored, confirmed, and still largely unaddressed. The arithmetic has run in one direction for 70 years. Here is what the research now shows about running it in the other direction, and what a backyard garden can do in a single growing season that a 10,000-acre farm cannot do in a decade. In 1999, Gabe Brown sat in a meeting with his lender outside Bismarck, North Dakota. The bank had run the numbers. 4 consecutive years of total crop failure, hail in 1995, hail in 1996, late spring freeze in 1997, drought in 1998, had left him in deeper debt than the farm could service. His soil organic matter had been tested earlier that year at 1.7%. The bank's position was straightforward. It could not extend credit for another conventional planting season. He could not afford the synthetic inputs he had always purchased. He could not afford the fuel for tillage. He could not afford to do anything he had previously done. What he did instead, out of pure financial desperation, with no philosophical framework, no community of regenerative agriculture advocates, no books on soil biology, was plant cover crops. Crimson clover, hairy vetch, tillage radish. The seed was inexpensive. He had nothing else. He did not till because he could not afford the diesel. That autumn, Brown ran a soil test. The number came back, 1.7%, exactly the same as the year before. He had done everything differently. The soil hadn't noticed yet. He stood in the field holding the results, deeply in debt, with a winter coming, and no evidence that anything he had done had worked. Most people would have stopped. Brown couldn't stop. The bank had already made that decision for him. He kept going. By year 3, the number moved. Slightly. By year 5, faster. By year 12, it had crossed 7%, a level researchers in his region had not previously documented on any field that had ever been conventionally managed. Then, in 2012, a soil scientist visited his property to conduct a routine soil infiltration test, a standard measurement of how quickly water moves through the soil profile. On the neighboring conventionally tilled farms, the test produced the regional norm of approximately half an inch of water infiltration per hour. On Brown's land, the test showed 9.5 inches per hour. The scientist ran the test twice. His equipment was working correctly. Brown's soil had recovered its biological structure to a degree researchers had not previously measured on formerly depleted American cropland. 9.5 inches an hour. On land that had been weeks from foreclosure with 1.7% organic matter 18 years earlier, the equipment was fine. The soil had simply become something it had not been in living memory. Stop for a second, because what comes next is the most important part of this video. Not for Brown's farm, for your backyard. What makes Brown's case usable for the gardener watching this is not the result. It is the sequence. He documented what changed and in what order, and the order matters more than any single product or amendment. Reversal 1. Stop breaking the network. Brown's first unintentional contribution to his own recovery was stopping tillage. Tillage destroys the mycorrhizal network, the same fungal system synthetic fertilizer had already begun atrophying. A single tillage pass can set back mycorrhizal recovery by months. The no-till decision Brown made out of financial desperation was, biologically, the most important single action he took. The network began rebuilding before any amendment was added. The mistake most gardeners make here is the opposite of what you'd expect. When a backyard gardener decides their soil needs help, their first instinct is to dig, fork, or rototill, to improve the soil by working it. This destroys precisely the biological infrastructure they are trying to rebuild. Start by stopping the disruption. Add to the surface. Let the biology integrate it downward on its own schedule. Reversal 2. Feed the system, not the plant. Cover crops, specifically leguminous species like crimson clover, hairy vetch, and Austrian winter peas, restore biological nitrogen fixation. One season of crimson clover can add 80 to 200 pounds of biologically fixed nitrogen per acre without any purchased input. But the nitrogen is secondary. The primary function is feeding the microbial population. Cover crop roots release exudates, sugars and amino acids that feed bacteria and fungi in the rhizosphere. The soil food web wakes up. The precision detail, clover must be cut or turned in at the flowering stage before it sets seed. A cover crop that goes to seed becomes next year's weed problem. Timed correctly, it is the free nitrogen and biology cycle that Ulbrecht documented as the foundation of healthy soil, still functioning exactly as he described, still free of charge. Reversal 3. Rebuild the fungal network directly. Mycorrhizal inoculants. Direct application of the fungal partners that synthetic fertilizer atrophied. University trials show measurable mycorrhizal recovery in depleted soil within one growing season of inoculant application, combined with organic matter input. For a backyard garden, this costs under $20 for a full season's treatment. It is the single most cost-effective intervention available. Here's what that means for your garden right now. The first application of compost to a conventionally managed soil bed does not add nutrients. It adds organisms. The nutrients follow in the second season, the third, and the fourth. Understanding this one distinction is the difference between a gardener who tries biological methods once and abandons them, and a gardener who builds soil that feeds them for the next 20 years. There is an unpopular position embedded in this video that should be stated directly. Restoring soil biology in a backyard garden is not a weekend project. Brown's recovery in North Dakota took 20 years to reach full productivity. The first measurable change came in year 3. A backyard gardener starting today will see meaningful biological improvement in the first season, but they will not see full recovery in 2 seasons. The honest answer is 3 to 5 years of consistent biological input before a garden managed conventionally for years returns to something approaching its original productive capacity. If your yields have been dropping and you've been adding more fertilizer without seeing results, this is why. The soil is not responding to inputs the way it once did, because the biology that processes those inputs is no longer adequately present. You are not doing something wrong. You are experiencing the endpoint of a cascade that began long before you planted a seed in that soil. This is not a reason not to start. It is a reason to understand what you are starting and to start now rather than next season, because every growing season that passes is a season of recovery that cannot be recovered. Two interpretations of the synthetic fertilizer record deserve to sit alongside each other before this conclusion lands. The first, synthetic fertilizer was a net positive for human civilization. It fed billions who would otherwise have gone hungry, and its soil biology costs are manageable with regenerative practices we now understand. The second, synthetic fertilizer solved a short-term yield problem by creating a long-term soil dependency problem, and the cumulative nutritional cost, declining crop nutrient density across 70 years, represents an unacknowledged public health debt that is still being paid. Modern soil science has not reached consensus on the exact reversibility timeline for severely depleted ground, and both interpretations have legitimate evidence behind them. The roots and garden position is that both interpretations are partially true, and the most important point sits between them. The measurement system that made one cost visible and the other invisible is the part of this history that has never been adequately examined. The roots and garden position on synthetic fertilizer itself is this: it did not fail. It succeeded at precisely what it was designed to do: maximize yield from a specific set of inputs over a short time horizon. The failure was in the measurement system that treated yield as the only variable worth optimizing. A garden that produces abundantly for 2 years and then requires increasing input to maintain the same yield is not a productive garden. It is a garden running on borrowed fertility. Albrecht knew this in 1952. The soil in your backyard has been paying interest on that loan ever since. Here's the detail that changes how you think about timelines. In 1978, a soil scientist named Gary Zimmer was farming on land in Walton, Wisconsin that had been conventionally managed for 30 years. His soil organic matter tested at 0.8%. Zimmer calculated that, to restore it to 3%, considered the minimum for biologically functional soil. At the rate organic matter naturally accumulates in undisturbed land would take approximately 100 years. He did it in 11. Documented program, cover crops, compost, nobelium synthetic input. The arithmetic of restoration is not comfortable. It is also not hopeless. It is, at the small scale of a backyard garden, considerably faster than the arithmetic that took Zimmer 11 years on a Wisconsin farm. The same biology applies. The same sequence works. Gabe Brown's soil organic matter, from 1.7% in the late 1990s to over 11% by 2018, 20 years, on a North Dakota farm that was weeks from foreclosure when the process began. A standard backyard garden can show measurable biological recovery in a single growing season. It will not reach 11% in one season. It can begin moving in that direction. The arithmetic runs in both directions. The reason to start now is that starting later costs a season you cannot recover. Gabe Brown's farm outside Bismarck, North Dakota is still producing. The infiltration test that the visiting scientist ran twice, 9.5 inches per hour. The soil organic matter, stable above 11%. The input costs at a fraction of neighboring operations. The bank that nearly foreclosed in 1998 is no longer involved in his operation in any meaningful way. He has given that bank nothing left to hold. This is not a philosophical statement. It is a documented agricultural outcome on specific American land, in a specific American state, recorded by a specific American farmer who kept records from the first failing season to the last soil test. The viewer's backyard is smaller than his farm. The same biology applies. It runs more slowly on smaller land in some respects, and faster in others. A backyard gardener can apply organic matter at a density per square foot that a commercial operation cannot afford. The arithmetic of recovery is available to anyone with a soil test kit, a bag of cover crop seed, and 3 to 5 years. There is a specific patch of ground in central Virginia, and one in central Ohio, and one in upstate New York, and one in every state where this video is being watched, that has been receiving fertilizer and producing food for years, and quietly losing something irreplaceable the entire time. The man or woman tending that ground does not yet know what is missing. They are about to, not the science, Not the cascade, not the institutions, just the soil itself, under the garden, under their feet, that has been losing something it could not tell them about, year after year while they were feeding it the wrong food. The losing doesn't stop on its own. It stops the moment someone decides to change the system underneath their feet. The roots and garden position on what follows is simple. You cannot restore in one season what was depleted over 70 years. You can begin the cascade in the other direction. Beginning is the part that matters. If this changed the way you see your soil, even slightly, subscribe. Because what's under your garden is only the beginning of this story. Did synthetic fertilizer save American agriculture in the 20th century? Or did it purchase short-term yield by spending biological capital that will take generations to rebuild? And does your answer change what you put on your garden this spring?